Inside a neutron star, matter is pushed so far beyond ordinary limits that atoms vanish, nuclei deform, and even neutrons may begin to lose their identity. These tiny dead stars are only the size of a city, yet they can hold more mass than the sun, balanced on the last thin edge before becoming a black hole. Tonight, the journey moves beneath the surface, through crushed crusts, nuclear pasta, impossible pressure, and the hidden core where physics may be forced to reveal something new. Before the story begins, thank you for spending your time here. If this kind of calm science journey helps you relax, learn, or drift into sleep, please like the video, subscribe to the channel, and share it with someone who loves the mysteries of the universe. And quietly, before we go deeper, what time is it where you are, and where are you watching from? Leave a comment below. Now, let us begin our descent into the impossible matter inside a neutron star. The Crab Nebula still carries the shape of a stellar death, its filaments spread outward like torn threads of gas, lit by the energy of what remains at the center, where a collapsed core turns with a regularity that seems almost too precise for something born in violence. The object there is not a normal star. It is not burning hydrogen in a familiar core, not shining because fusion still holds gravity and balance. It is the remnant left behind after that balance failed, a city-sized concentration of matter packed so tightly that the old meanings of surface, weight, and solidity begin to lose their usefulness. This is where the subject has to begin, not deep inside the core, but at the boundary where the dead star first presents itself to the universe. A neutron star appears small only because distance hides the conditions written into it. Across only a few tens of kilometers, it can contain more mass than the sun. Its gravity is strong enough to turn falling matter into a weapon before it reaches the ground. Its magnetic field can gather radiation into narrow beams and sweep them through space like the pulse of a lighthouse. Its crust, if it can be called a crust in any ordinary sense, rests above material that has been compressed past the familiar states of matter and towards something that belongs less to chemistry than to nuclear physics. Nothing about such an object is mild, yet the tone of its existence is not simple destruction. It is a held catastrophe, a collapse interrupted at the last possible moment by laws that operate far below the scale of planets and stars. The first strangeness of a neutron star is that it exists at all. Gravity has already done almost everything it can do without forming a black hole. It has crushed the remains of a massive stellar core until atoms can no longer remain atoms in the usual way. It has driven matter inward until the space between particles, which gives ordinary objects most of their volume, has nearly vanished. A spoonful of this material, if it could be held outside the star without tearing itself and everything nearby apart, would carry the mass of a mountain, a city, or more. These comparisons are never quite enough, because the density is not simply large. It belongs to a regime where the familiar experience of matter no longer offers reliable intuition. On Earth, stone feels hard because its atoms resist being pushed together. In a neutron star, that kind of resistance has already been defeated. The electrons that once surrounded nuclei have been forced into conditions where the identity of ordinary atoms gives way to a much harsher arrangement. Protons and electrons can be driven together, leaving behind neutrons and a smaller fraction of charged particles, all pressed into a body whose surface gravity is so intense that height itself becomes an extravagance. A mountain on Earth rises because rock can support a slope against gravity. A mountain on a neutron star can rise only by fractions of a millimeter, because even the strongest crust cannot hold much shape under such a pull. The result is one of the smoothest solid surfaces expected in the universe. Although the word smooth should not make it sound gentle, it is smooth because gravity has knit it almost flat. It is stable because any excess shape is punished immediately by the weight of the star beneath it. The surface is not calm in the ordinary sense. It is controlled by force. Some neutron stars make this control visible through pulses. When a neutron star spins, its magnetic poles need not align with its rotation. Charged particles accelerate along magnetic field lines. Radiation escapes in beams, and if those beams cross Earth, observatories record a rhythm that may remain steady over years with astonishing precision. These pulses were once puzzling enough that their signal seemed almost artificial, not because they truly required an intelligent source, but because nature had produced a clock from a dead star. The regularity comes from the concentration of angular momentum. As a large star collapses, the rotation it once carried is squeezed into a much smaller body, the way a spinning skater turns faster when drawing in the arms. A neutron star can rotate many times each second, and some turn hundreds of times each second. Matter that once filled a stellar core now completes its rotation in less time than a blink. That speed is not an ornament to the star. It shapes the magnetosphere, the region around the star ruled by magnetic fields and charged particles. It helps decide how energy leaves the surface and how the remnant slowly loses its spin across time. In the most magnetic versions, called magnetars, the field becomes so powerful that it is not merely a surrounding feature. It becomes part of the star's internal stress. Magnetic energy can twist the crust, strain it, and occasionally release itself in violent flares. A starquake on such a surface is not like the shifting of tectonic plates across a planet. It is a fracture in a shell under conditions of extraordinary density, tied to magnetic fields capable of affecting atoms at a distance. Even before the interior is considered, the outside of the neutron star is already a place where common categories begin to fail. The atmosphere above it may be only a thin skin, far shallower than any planetary atmosphere, yet it can be heated to millions of degrees and squeezed to densities that make ordinary gases seem almost empty. Light leaving this environment does not travel away unchanged. The gravity is strong enough to stretch its wavelength, reddening the signal as it climbs out of the star's deep gravitational well. This effect gives astronomers one of the few direct clues to the star's compactness. Because the stronger the gravity at the surface, the more the escaping light is shifted. The dead star marks its own extremity on the radiation it releases. Even the path of light bends around it. Parts of the far side can become visible, not because the star is transparent, but because space-time itself is curved around the mass. A neutron star is therefore not just a dense object sitting in space. It changes the geometry near it. It forces light, matter, and time into a narrower range of behavior than ordinary stars allow. The surface is the first visible boundary of that distortion. Beneath it, the pressure rises so quickly that each downward step becomes a change in physics. Above it, telescopes receive pulses, thermal X-rays, bursts, and faint patterns that must be translated carefully into mass, radius, temperature, and magnetic field. The observer never holds a sample. The observer reads the surface as a message from an unreachable world. That message is difficult because a neutron star hides its most important facts. A normal star announces its interior through fusion, through light made by hot plasma and carried outward across immense layers. A neutron star is different. It is already the aftermath of fusion's failure. Its surface emission is a residue of heat, magnetic disturbance, accreted matter, and rotational energy. The deeper forces that support it are not easily visible. Yet those forces are the reason the star has not disappeared behind an event horizon. Somewhere under the thin atmosphere and crushed crust, matter continues to resist gravity, not with the pressure of hot gas alone, but through quantum rules and nuclear interactions, the surface shows the consequence, not the full cause. This distinction matters because a neutron star is often described by its extremes, but its deeper importance lies in the balance between extremes. It is not simply heavy, it is heavy and still finite. It is not simply collapsed, it is collapsed and still held open. It is not merely strange. It is strange because known physics is being asked to work in a place where almost every ordinary form of matter has already been stripped away. The boundary between a neutron star and a black hole is therefore not only an astronomical boundary, it is a question about what pressure can be, what particles become when crowded too closely, and whether the laws that keep matter from occupying the same state can resist the most concentrated gravity that stars can produce. On the surface, this question is disguised as a compact, spinning remnant, perhaps a pulsar ticking in a radio telescope or an X-ray source on the edge of detection. But the real question lies in the fact that the star still has a surface at all. A black hole has no material surface from which light can depart. A neutron star does, however hostile and compressed that surface may be. It remains a place where matter has not fully surrendered. The dead star has crossed beyond the life of ordinary stars, beyond the stability of familiar atoms, beyond the pressures that shape planets or white dwarfs, and still something stops the inward fall. The surface is therefore not the end of the story. It is the first sign of a deeper resistance, a thin visible limit above a buried contest between gravity and matter at its most severe. To understand what stands there, holding collapse away from oblivion, the narration has to move backward from the dead star's face to the balance that living stars once maintained, because only by seeing how ordinary stellar matter avoids collapse can the neutron star's impossible survival begin to make sense. The sun holds itself together through a balance so ordinary in appearance that its violence is easy to miss. From Earth, it seems steady, a familiar disk rising through haze, burning with a patience that has shaped every day of human history. Yet inside it, every layer is taking part in a continuous negotiation between outward pressure and inward gravity. The surface light carries no visible sign of this contest. It arrives softened by distance, filtered through atmosphere, made gentle by habit, but beneath the photosphere, beneath the churning plasma and the slow movement of heat through the solar interior, the star is only stable because collapse is being resisted second by second. Gravity pulls all solar matter inward toward the core. It does not pause, and it does not need a trigger. It is always present, always drawing mass toward mass, always asking the star to become smaller. Against it stands pressure, created by heat and by the energy released as hydrogen nuclei fuse into helium. This is the great internal arrangement known as hydrostatic equilibrium, a phrase that sounds calm because the balance is successful. The calmness is deceptive. It is not the absence of force. It is the equality of enormous opposing forces, each one large enough to define the entire structure of the star. In the solar core, matter has already entered a state far removed from everyday gas. The temperature is high enough to strip electrons from many atoms, creating plasma, a charged mixture of nuclei and free electrons that behaves according to electric fields, magnetic fields, pressure, radiation, and motion. The core is also dense, not by the standards of neutron stars, but far beyond any ordinary flame or atmosphere. Hydrogen, the lightest element, is crushed under the weight of the layers above it, until particles meet often enough for nuclear fusion to become possible. Fusion is not easy. Protons repel one another because they carry the same electric charge. To join them, the solar core must bring them close enough for the strong nuclear force to take over, and even then the process depends on quantum behavior that allows particles to cross barriers they could not overcome in a purely classical world. The sun therefore shines because gravity compresses its center until matter reaches the conditions where nuclear physics can release energy. The outward pressure from that energy does not eliminate gravity, it answers it. If the core grows slightly hotter, fusion becomes more active, pressure rises, and the star expands a little, cooling the core. If the core cools, pressure weakens, gravity compresses it, and fusion rises again. The star is not a rigid object but a self-regulating body, maintaining its form through feedback. This is the first lesson that living stars offer before the descent into neutron stars begins. Matter survives under pressure by finding a way to push back. In a main sequence star like the Sun, the resistance comes from heat, radiation, and fusion. The equation of state describes this relationship in mathematical form, linking pressure, density, and temperature so that the star's structure can be understood layer by layer. The phrase may sound technical, but the idea is direct. It asks how matter responds when it is squeezed, heated, or allowed to expand. In the Sun, the answer is known with remarkable confidence because the star is close enough to study in detail. Its surface vibrates with waves that reveal interior conditions. Neutrinos born in the core pass outward almost untouched, carrying news from the fusion region long before light can diffuse to the surface. Together, these signals show a star that remains stable because its equation of state is strong enough under solar conditions to let pressure keep pace with gravity. The same question follows every star across its life. What happens when matter is pressed harder? What kind of pressure appears? How long it can hold? In small and medium stars, the answer changes slowly over billions of years. Hydrogen in the core becomes helium. The available fuel diminishes. Fusion does not simply stop everywhere at once, but the central arrangement begins to shift. The core contracts as hydrogen is exhausted there, while shells around it may continue burning. The outer layers expand, the surface cools, and the star becomes a red giant. This expansion is not a release from gravity. It is another consequence of the internal balance being rearranged. The core, deprived of its original fuel, cannot support itself in the same way, so it contracts until new temperatures and pressures allow helium fusion to begin. For a time, another equilibrium can be found. The star discovers a new form of internal support, and gravity is delayed again, but each delay comes at a cost. Fusion builds heavier elements, and the structure becomes layered, with different reactions taking place in different shells if the star is massive enough. The deeper the sequence goes, the less energy is gained from each step. Hydrogen to helium provides the long, bright foundation. Helium can become carbon and oxygen. In larger stars, still heavier nuclei can form, but the chain does not continue forever. Iron stands near the end of the useful path, not because iron is rare or fragile, but because its nucleus is tightly bound. Fusing iron does not release energy in the way earlier reactions do. It demands energy instead. For a massive star, this is the crucial change. The core can no longer count on fusion as its source of outward pressure. A living star has spent its existence using nuclear reactions to answer gravity. When the core becomes dominated by matter that cannot provide that answer, the old balance fails with a suddenness that belongs to stellar interiors rather than human timescales. The collapse of a massive core is not simply the star falling inward like a building. It is a physical transition in which the equation of state changes because the material itself changes. Electrons are driven into protons. Neutrinos are produced in overwhelming numbers. Atomic nuclei are compressed until their separation becomes difficult to maintain. The star has crossed from ordinary stellar pressure into a regime where quantum pressure and nuclear density become decisive. The outer layers, still carrying the memory of a luminous star, are no longer supported by the core beneath them. They fall inward, rebound, and are driven outward in a supernova, scattering newly made elements into space. The event is bright enough to mark galaxies, yet the most important action for the future neutron star is hidden at the centre, where the collapsed core either finds a new resistance or continues past every boundary into a black hole. This is why the peaceful sun matters to the story of impossible matter. It shows the first version of the contest in its most familiar form. Gravity presses, matter responds. The kind of response decides the fate of the object. In the sun, pressure from hot plasma and fusion holds the core open. In an aging low-mass star, that support eventually gives way to another kind of pressure in a white dwarf. In a massive star, even that path can be exceeded, forcing particles into still more extreme arrangements. The neutron star is not an isolated curiosity. It is the late answer to a question that every star has been asking since it first ignited. How can matter remain extended when gravity wants it compressed? The answer changes with density. It changes with temperature. It changes with the particles available and with the quantum rules they obey. When fusion is abundant, the star glows and lives. When fusion can no longer carry the burden, gravity exposes deeper layers of physics. What looks like death from outside is also a search for another form of support. A supernova is therefore both an ending and a test. It destroys the old star, but it also reveals whether matter has one more way to resist. The living star's balance has failed, yet the collapse does not always reach oblivion. In some remnants, the core stops again, not because heat saves it, and not because fusion returns, but because the particles themselves are forced into a quantum arrangement where crowding becomes resistance. Before that final neutron-rich state can be understood, the path passes through a quieter but essential object, the white dwarf, where the first great quantum safety net appears, and where matter learns to resist gravity after starlight has nearly gone out. Sirius B is almost hidden by the brilliance of its companion, yet its faint light carries one of the most important lessons in stellar death. It is small, hot, and dense in a way that ordinary stellar gas cannot explain. The object is called a white dwarf, and it represents the future of stars that are not massive enough to make neutron stars directly. It is not a star in the living sense, because fusion no longer supports it in the old way. It is the exposed core left behind after outer layers have drifted away. A compact ember made mostly of carbon and oxygen, shining because it still retains heat from its former life. At first glance, a white dwarf seems like a gentler remnant than a neutron star. It is roughly planetary in size rather than city-sized. Its gravity is extreme but not quite the same final warning. Its matter is dense beyond ordinary rock, but not yet pressed to the density of an atomic nucleus. Yet the white dwarf is not a minor stop on the road to stranger objects. It is where the first great quantum support appears, the point where matter can no longer be understood as merely hot particles pushing outward. In the sun, the core resists gravity through thermal pressure and fusion. In a white dwarf, the fuel has largely gone quiet. Heat still leaks away, but cooling does not cause the remnant to collapse in the ordinary way. Something else holds it open, and that something comes from the rules that govern particles rather than from the fire that once made the star shine. The key is the electron. In ordinary atoms, electrons occupy regions around nuclei, shaping chemistry, hardness, colour, and the difference between one element and another. They are light particles, small in mass compared with protons and neutrons, but their behaviour is controlled by quantum mechanics. They belong to a class of particles called fermions, and fermions obey the Pauli exclusion principle. This rule says that no two identical fermions can occupy exactly the same quantum state at the same time. The statement is simple, but inside a dying stellar core it becomes a form of pressure. When matter is squeezed, the electrons are forced into a smaller and smaller volume. The lowest available quantum states fill first. Once those states are occupied, additional electrons cannot join them. They must take higher energy states, not because the material is hot in the usual sense, but because the available quantum room has been used up. Compression therefore creates resistance even when ordinary heat is no longer enough. This resistance is called electron degeneracy pressure. The word degeneracy does not mean decay or weakness here. It describes a situation in which the particles are crowded into a dense quantum arrangement, filling available states according to the rules of their identity. The pressure that follows is unlike the pressure of a gas in a balloon. A hot gas pushes outward because its particles move rapidly and collide often. If it cools, the pressure falls. Degenerate matter is different. It can remain supported even as it cools, because its resistance is rooted in exclusion. Gravity may try to push every electron into the lowest possible condition, but the rules do not allow it. Each electron must keep its own quantum place. This is why a white dwarf does not simply fade into a smaller and smaller point as it loses heat. Its survival is not a matter of warmth alone. It is a matter of forbidden sameness. The stellar remnant is held apart by a principle that has no familiar counterpart in everyday experience, although its effects make ordinary matter possible as well. In a white dwarf, that principle is no longer subtle. It becomes the architecture of the star. The density is high enough that atoms cannot remain neatly arranged as they do in a solid. Nuclei sit in a sea of electrons that has been compressed until quantum pressure dominates the structure. The material may be described as matter, but it is not matter as chemistry knows it. It is a dense remnant in which the nuclei provide most of the mass, while the electrons provide much of the pressure. That division matters because it sets a limit. Electron degeneracy pressure can be strong, but it is not infinitely strong. As more mass is added to a white dwarf, gravity grows more severe. The electrons must occupy still higher energy states to resist the compression. Eventually, the resistance approaches a boundary where the electrons are moving at speeds that require relativity to be included. At that stage, adding mass no longer strengthens the support in the same way. The remnant nears the Chandrasekhar limit, the maximum mass that electron degeneracy pressure can support in a white dwarf, roughly 1.4 times the mass of the Sun. This limit is not a decorative number in astrophysics. It is a hinge between endings. Below it, a white dwarf can remain stable for immense periods, cooling slowly into darkness. Above it, electron degeneracy pressure fails to answer gravity. The object cannot remain a white dwarf. For a star in a binary system, this boundary can be approached if material flows from a companion onto the white dwarf. The increase may look gradual from outside, but the internal consequence is sharp. Once the mass crosses the allowed range, the remnant can ignite runaway nuclear reactions and tear itself apart as a type of supernova, or in other contexts collapse toward a denser state. The same quantum safety net that seems so firm below the limit becomes powerless above it. This is the pattern that will return in harsher form inside neutron stars. A support mechanism works only within a certain domain. Pressure is not a single universal answer. It has conditions. And gravity is patient enough to find them. The history of white dwarfs therefore prepares the mind for neutron stars in two ways. First, it shows that dead stellar matter can be supported without active fusion. A remnant can survive through particle rules that were invisible during most of the star's luminous life. Second, it shows that every form of support has an upper boundary. The existence of a limit means that stellar death is not one path, but a branching set of possible outcomes. A core below one threshold becomes a white dwarf. A core that exceeds that threshold may be driven deeper into a regime where electrons and protons can no longer remain separate in the familiar way. The white dwarf is not the final form of compressed matter. It is a warning that quantum mechanics can delay collapse, and also a warning that delay is not the same as escape. The relation between mass and size in a white dwarf already feels contrary to ordinary intuition. Adding mass can make the object smaller, because stronger gravity compresses the degenerate electron sea more tightly. In normal objects, adding material usually means making something larger. In degenerate stars, more mass can mean less radius. The remnant responds not like a pile of matter, but like a quantum system under pressure. This inversion becomes even more severe in neutron stars, where matter is pushed beyond electron degeneracy into something closer to nuclear density. Yet white dwarfs remain understandable enough to serve as a bridge. Their physics is strange, but it still rests partly on identifiable nuclei and electrons. Their surfaces can be modelled, their masses and radii can be measured. Their role in stellar evolution can be traced across clusters and binary systems. They stand as compact laboratories for the first stage of matter, after ordinary stellar support has vanished. Inside them, the cosmos demonstrates that collapse can be stopped by a rule, not by a flame. That insight changed the meaning of a dead star. A remnant no longer had to be seen as a cooling fragment only. It could be a place where the microscopic identity of particles determined the fate of a macroscopic object. The pressure holding up a body the size of a planet was written into the behavior of electrons, particles so light that they barely contribute to the star's mass. This scale crossing is one of the quiet marvels of astrophysics. A law discovered in the realm of atoms becomes the reason a stellar corpse does not vanish. But when the mass is too great, even this elegant support cannot remain. Gravity presses beyond the electron sea, beyond the white dwarf limit, into a more violent transformation where the charged particles that once defined atoms are forced to merge. The next object is smaller, denser, and far less forgiving. The white dwarf shows that quantum pressure can catch a dying core once. The neutron star begins when that first catch fails, and matter is driven to discover whether a deeper rule can hold it back again. The birth of a neutron star begins before the supernova becomes visible. In the last hidden moments of a massive star, the central core is no longer a furnace that can bargain successfully with gravity. It has built heavier and heavier elements through successive stages of fusion, until the inner region approaches iron-rich material that cannot give the star a useful new source of energy. The old pattern has reached its last stable form. For millions of years, then thousands, then far shorter intervals near the end, fusion has kept finding temporary ways to answer the inward pull. Now the answer runs out. The core continues to carry the weight of the star above it, but the pressure available to resist that weight is no longer enough. Electrons, nuclei, heat, and radiation are all forced into a rapidly tightening volume. The collapse is not slow in the way a surface observer might expect from the long life of the star. It accelerates with a speed that belongs to gravity once its main opposition has been weakened. What had been a central engine becomes a falling interior. The material does not merely move inward, it changes identity as it falls. This is the essential difference between a collapsing core and an ordinary dense object. The star is not just packing the same matter into less space, it is passing through thresholds where the particles themselves are rearranged. At first, electron degeneracy pressure, the same quantum resistance that supports white dwarfs, tries to hold the line. Electrons fill their available states, push back against compression, and delay the inward motion. But if the core is massive enough, The Chandrasekhar limit has already been exceeded. The electron sea cannot provide a stable floor. Gravity continues to squeeze, and the electrons are driven into protons. The process is called electron capture, and it turns charged particles into neutrons while releasing neutrinos. In ordinary matter, electrons and protons remain distinct, separated into the architecture of atoms. In the collapsing core, that architecture has no room left. The atom is no longer the unit that matters. The relevant scale has shifted inward to the nucleus, and even the nucleus is about to lose its familiar boundaries. Electron capture does two things at once. It reduces the number of electrons available to provide pressure, and it fills the core with neutrons. This makes the collapse more severe. Because one support is being removed while gravity is still pressing harder, it also floods the interior with neutrinos, ghostly particles that normally pass through matter with ease. In the Sun, neutrinos escape from the core and offer a direct clue to fusion. In a collapsing massive star, they are produced in such astonishing numbers and under such dense conditions that even they can become briefly trapped. The core grows so compact that matter becomes opaque to particles that ordinarily cross entire planets as if nothing were there. This trapping matters because the neutrinos carry energy and lepton number, properties that influence the dynamics of the collapse and the later explosion. Yet at the deepest centre, the most immediate question is simpler. How far can the material fall before it meets a new resistance? As the density climbs toward nuclear density, individual nuclei are pressed so close together that the distinction between one nucleus and the next begins to blur. The core approaches the density found inside atomic nuclei, but now that density extends across an object kilometers wide. This is a staggering change of scale. A density that normally belongs to a microscopic speck becomes the condition of a stellar remnant. Matter has moved from the world of chemistry, past the world of ordinary plasma, through the domain of degenerate electrons, and into a state where neutrons dominate the response. At this point, the collapse stiffens. Neutrons are also fermions, which means they obey the Pauli exclusion principle. They cannot all be forced into the same quantum state. As they are crowded together, neutron degeneracy pressure begins to rise. Nuclear forces also become important, because neutrons at very short range do not behave like passive grains being poured into a pit. Their interactions can resist further compression. The inward fall encounters a wall made not of stone, not of heat, but of quantum exclusion and nuclear repulsion. The central core halts and rebounds slightly. This rebound alone is not the full explanation for a successful supernova, because the shock wave that forms can stall as it loses energy, breaking apart in falling nuclei and fighting through the star. Neutrinos are likely crucial in reviving that shock, depositing some of their energy into the matter behind it. The details remain one of the difficult problems in stellar astrophysics, with simulations still exploring how rotation, turbulence, magnetic fields, and neutrino transport work together. But the broad transformation is clear. The core collapses until ordinary support fails, then reaches densities where neutron-rich matter can push back. Around it, the outer layers of the star are driven outward in a vast explosion, seeded with elements and shaped by the violence of the collapse below. To the surrounding galaxy, the supernova is the visible event. To the remnant, it is the shedding of everything that can no longer belong to the compact core. What remains is startlingly small. The star that once filled a region millions of kilometers across leaves a remnant perhaps only a few tens of kilometers wide. Its mass is comparable to that of the Sun, but its radius resembles the scale of a city. The collapse has concentrated not only matter but also rotation and magnetic field. A core that once turned at moderate pace can become a rapidly spinning neutron star because angular momentum is conserved as the radius shrinks. Magnetic field lines, drawn inward with the collapsing material, become compressed as well, leaving fields far stronger than those of ordinary stars. The newborn remnant is hot, dense, and restless. Its crust has not yet settled into the cold rigidity expected later. Its interior is cooling through neutrino emission. Its outer layers may be shaped by fallback, as some material from the explosion fails to escape and rains back down. The object is not born as a quiet sphere. It is born as an aftermath still rearranging itself. Yet the decisive point has already happened. The collapse has stopped short of a black hole. The remnant has found a new form of support, neutrons, together with a smaller population of protons, electrons, and perhaps other particles at greater depth, now form the main body of the star. The name neutron star is therefore both useful and incomplete. It identifies the dominant transformation, but it does not settle the interior. Even at birth, the star contains layers, gradients, and uncertainties. The outer crust may still include neutron-rich nuclei arranged under enormous pressure. Deeper down, free neutrons appear. Deeper still, the core may hold material whose exact composition depends on the equation of state. But before those hidden layers can be explored, the birth itself has to be understood as a crossing of limits. The living star lost thermal and nuclear support. The white dwarf form was unavailable because the mass was too high. Electrons were captured. Neutrons appeared in overwhelming numbers. A nuclear density object emerged from the collapse. This sequence is not merely a story of destruction. It is a demonstration that matter has multiple defenses, each revealed only when the previous one fails. There is a solemn order to it. Fusion holds first. Electron degeneracy can hold later, but only below its mass limit. Neutron degeneracy and nuclear forces hold deeper still, but only for remnants that do not become too massive. A neutron star is the result of that third defense becoming visible. It is the universe discovering, under extreme pressure, that matter has one more way not to vanish. The supernova remnant may expand for centuries, its gas shining in delicate filaments, while the compact object at its center spins and cools. The outward cloud records the violence of the star's death. The neutron star records the part of the collapse that did not continue. This makes it a threshold object, suspended between the stellar and the relativistic, between nuclear matter and gravitational catastrophe. It has a surface, yet that surface lies above matter, compressed close to the limit of what particles can bear. It has mass, radius, and rotation. Yet every one of those ordinary measurements points back to a hidden question about the pressure inside. The birth of the neutron star explains why the object is so extreme, but it does not explain what its layers become afterward. Once the explosion has cleared and the remnant settles into its long, cooling existence, the next mystery begins not in the blaze of formation, but just beneath the thin atmosphere, where the first solid boundary of the dead star hides matter, unlike any crust on Earth. A neutron star does not need a deep atmosphere to separate itself from space. The outermost gases may rise only a handspan above the surface, a skin of hydrogen or helium so thin by planetary standards that it would barely count as weather, yet so compressed and heated that it belongs to no ordinary idea of air. In that narrow layer, gravity has already done much of its sorting. The lightest elements float at the top, not because the environment is gentle, but because heavier nuclei settle downward with extraordinary speed under the pull of the star. The result is a surface covering that can be shallow, hot, and almost impossibly dense at the same time. It is the first veil through which radiation must pass before it escapes to telescopes. Every photon leaving it carries some memory of temperature, gravity, magnetic field, and composition, although those memories are difficult to separate from one another. The atmosphere is therefore not a scenic boundary. It is an interpreter. changing the light that astronomers use to infer the size and compactness of the object beneath it. Below that thin layer, the star stops resembling anything atmospheric at all. The material becomes a crust, but the word crust has to be handled carefully. On Earth, a crust is rock, mineral, fracture, and movement over a mantle. On a neutron star, the crust is a lattice of atomic nuclei immersed in a sea of electrons, forced into existence by pressure so severe that chemistry has almost no role left to play. At the outer edge, nuclei may still be recognizable as nuclei, though often far richer in neutrons than stable atoms on Earth. The electrons around them are not bound into ordinary shells, shaping molecules and solids. They are squeezed into a degenerate fluid, moving through the lattice and helping carry electric current and heat. The material may behave like a solid in some ways, but it is a solid governed by nuclear density from below and gravitational force from above. It is not stone hardened by cooling. It is matter locked into place because every possible freedom has been narrowed. The descent through this outer crust is a descent through increasing pressure rather than through familiar layers of rock. Each step downward brings nuclei closer together. Electrons grow more energetic because they're confined to smaller volumes, and their rising energy changes which nuclei can survive. Some electrons are captured by protons inside nuclei, turning them into neutrons and making the nuclei more neutron-rich. In a laboratory on Earth, many such nuclei would be unstable and decay quickly. Inside the crust, the environment changes the rules of endurance. The pressure and electron sea make exotic nuclear arrangements possible, at least for as long as the star holds them in place. This is one of the quiet difficulties in understanding neutron stars. The crust contains forms of matter that may not be long-lived anywhere else, so experiments can only approach them indirectly. Nuclear physics on Earth studies rare isotopes and dense matter in fragments, while the star assembles them across an entire global shell. The outer crust still has nuclei as its landmarks, but those landmarks become stranger as the density rises. The lattice is not empty between them. It is threaded by electrons that have become highly relativistic, meaning their motion approaches speeds where Einstein's physics matters. Heat moves through this environment in ways shaped by both particles and magnetic fields. If the neutron star has a powerful magnetic field, the flow of heat can become uneven, making some surface regions hotter than others. These hot regions are important for telescopes such as NICA, because as the star rotates, warmer areas move in and out of view, creating patterns in X-ray brightness. Those patterns can reveal the star's radius and mass, but only if the atmosphere and crust are modelled with care. The surface is not a simple glowing ball. It is a compact relativistic object whose light is bent by gravity, filtered through a thin atmosphere, and influenced by magnetic structure. The crust beneath it becomes part of the observation even when it cannot be seen directly. It stores heat, guides currents, anchors magnetic fields, and determines how the surface responds to stress. This is especially clear in magnetars, where the magnetic field can be strong enough to deform the crust and store energy in twisted field lines. When that stress shifts, the crust may fracture or rearrange, releasing bursts of radiation. The event is sometimes called a starquake, though the comparison with earthquakes can mislead. Earthquakes occur in rock plates under planetary gravity. A magnetar flare is tied to a rigid nuclear crust, immense magnetic stress, and a gravitational field that allows almost no vertical relief. The crust is thin compared with the whole star, yet it can control visible outbursts because it is the place where the hidden magnetic interior touches the observable surface. It is also the region where the star's apparent smoothness conceals tension. Gravity flattens the surface so strongly that mountains can be tiny. but the crust can still sustain small distortions. Those distortions matter because any uneven mass on a spinning neutron star may emit gravitational waves, faint ripples in space-time. The crust's strength therefore limits not only the shape of the star, but also the kinds of signals it might send across the universe. A stronger crust could support larger irregularities. A weaker one would yield sooner, smoothing itself under gravity's demand. This turns the crust into a bridge between nuclear physics and astronomy. The microscopic strength of dense matter determines whether a star can carry a mountain, whether that mountain can disturb space-time, and whether future detectors might notice the disturbance. The surface may look like the outermost part of the object, but scientifically it is a testing ground for the behavior of matter under conditions that cannot be reproduced at human scale. As the descent continues, the nuclei become more crowded and more neutron-rich. The electrons keep being pressed into higher energies. Eventually a threshold is reached where neutrons can no longer remain confined inside nuclei. They begin to drip out into the spaces between them, creating what physicists call neutron drip. This phrase sounds almost gentle, but the change it describes is severe. It marks the transition from the outer crust to the inner crust, where nuclei coexist with a sea of free neutrons. The material has not yet become the uniform neutron-rich fluid expected deeper inside the star, but it is no longer an ordinary lattice of nuclei and electrons. The star has entered a mixed state. Some neutrons remain inside nuclear clusters, others move through the crust, and under the right conditions may form a superfluid, a state in which particles flow without ordinary viscosity. This matters for one of the strangest observable behaviors of pulsars glitches. Many pulsars slow down gradually as they lose rotational energy, but sometimes their rotation suddenly jumps, as if the star has adjusted itself from within. One leading explanation involves angular momentum stored in a superfluid neutron component beneath the crust, which can exchange motion with the solid outer layers. The exact details remain active research, but the implication is already striking. A small timing irregularity measured by a radio telescope may be connected to the hidden motion of neutrons beneath a crust that is only a narrow fraction of the star's radius. The crust is therefore not just a shell. It is a mechanical system, a thermal blanket, a magnetic anchor, and a participant in the star's rotation. Its behavior affects how the star cools, how it flares, how it spins, and how its interior communicates with the universe. Yet it is also only the beginning of the descent. Beneath the neutron drip line, the separation between nuclear clusters and free neutrons becomes harder to maintain in familiar terms. The pressure continues to rise. The nuclei are squeezed into arrangements that may no longer prefer round shapes. The competition between nuclear attraction, electric repulsion, neutron excess, and gravity begins to sculpt matter into forms that have no counterpart on Earth. The outer crust has already stripped atoms of their chemistry and replaced them with a lattice in an electron sea. The inner crust now prepares to deform the nuclei themselves. This is where the neutron star begins to reveal a deeper kind of impossibility. Matter is no longer merely dense, nor merely neutron-rich. It is being forced into geometry by pressure, taking on structures predicted by simulations rather than seen in laboratories. The atmosphere showed how thin the boundary with space can be. The outer crust showed how atoms lose their ordinary identity. The neutron drip region shows how even nuclei begin to surrender their internal confinement. What lies below is still solid in some sense, still structured, still able to bear stress, but its shapes are no longer the shapes of planets, minerals, or atoms. They are the first hints of nuclear pasta, the strange inner crust where matter may become the strongest and most distorted material known. The inner crust of a neutron star begins where the old roundness of nuclei becomes difficult to preserve. Above this depth, matter still keeps some memory of atoms, even if the atoms themselves have been stripped of their electrons and pressed into forms that would be unstable almost anywhere else. Below it, the pressure has risen high enough that neutrons leak out of nuclei and move through the spaces between them, changing the crust from a lattice of isolated nuclear clusters into a crowded mixture of clusters, electrons, and free neutron matter. The star is still not at its core. It has not yet reached the more uniform fluid expected deeper down, but the inner crust is already a region where shape becomes a physical question. A nucleus is not a tiny marble. It is a bound system of protons and neutrons held together by the strong nuclear force. While protons also repel one another through electric charge, in ordinary nuclei, these forces settle into compact forms. Inside the inner crust, the surrounding pressure begins to alter the compromise. Clusters are pushed close together. Neutrons fill the background. The usual boundary between one nuclear cluster and the next grows less meaningful. Matter is being asked to arrange itself under competing demands, and its answer may be nuclear pasta. The name is almost too playful for the conditions it describes, but it survives because it gives a human label to shapes that would otherwise be hard to picture. In simulations, the protons and neutrons do not always remain in separate round clusters. They can stretch into rods, flatten into sheets, open into tubes, or form bubbles of nuclear matter and void in patterns that resemble familiar food only in outline. The comparison does not soften the physics. It simply marks the fact that matter, when compressed close to nuclear density, but not yet made fully uniform, may prefer elaborate geometry. The reason is a balance of forces. The strong nuclear force favours holding nucleons close together. The electric repulsion between protons resists packing too much positive charge into one place. The surrounding neutrons and electrons change the energy cost of each possible arrangement. Gravity supplies the broader pressure that makes the compromise unavoidable. No single force alone draws the pasta. The structure emerges from their competition. Near one level, round clusters may be favoured. Deeper down, rods may reduce the energy. Farther still, sheets may become more stable, and then the pattern can invert into cylindrical or spherical voids before the matter finally blends toward the liquid core. These transitions are not like geological strata with clean boundaries. They are changes in the lowest energy arrangement of dense nuclear matter, shaped by temperature, composition, and pressure. What makes nuclear pasta important is not only that it may exist, it is that its existence could influence the behaviour of the entire star. A layer only a small fraction of the neutron star's radius may affect how heat moves, how the crust breaks, how magnetic fields evolve, and how neutrinos escape. The inner crust is thin on the scale of the object, yet the material inside it is so dense that thinness becomes misleading. A shallow layer can contain more mass than planets. A narrow shell can shape the signals that astronomers use to understand the remnant. This is one of the recurring inversions of neutron star physics. Small distances carry enormous consequences. A few meters downward can bring a meaningful change in particle behavior. A layer only hundreds of meters thick can weigh more than worlds. The ordinary link between size and importance has been broken. If nuclear pasta forms, it may be among the strongest materials in the known universe. Strength here means resistance to deformation before breaking. And simulations suggest that the interwoven nuclear structures could endure stresses far beyond ordinary solids. Steel is strong because metallic bonds allow atoms to hold together under strain. Diamond is hard because carbon atoms form a rigid crystal lattice. Nuclear pasta is held by forces acting inside and between nuclei. under compression so intense that its resistance may dwarf familiar materials by many orders of magnitude. Yet the word strong again needs caution. This is not a substance that could be mined, lifted, or shaped into an object, removed from the pressure of the neutron star. It would not remain stable in any ordinary environment. Its strength belongs to the prison that creates it. The star forces it into being, and only the star can keep it there. That dependence is part of the mystery. Nuclear pasta may be real inside neutron stars and nowhere else in a lasting form. The universe may be full of it in compact remnants, while no laboratory can display a sample on a table. For now, the evidence is indirect. Physicists model the interactions of protons, neutrons, and electrons under enormous density. They use nuclear theory, simulations, and observations of neutron star behavior to judge whether the pasta layers are likely. The challenge is that the inner crust sits in a regime where many details matter. The exact arrangement depends on the nuclear symmetry energy, which describes how the energy of nuclear matter changes when the balance between protons and neutrons shifts. It depends on temperature, especially in young neutron stars and merger remnants. It depends on impurities, defects, and whether the crust has had time to settle into its preferred state. A clean diagram may show round clusters becoming rods, rods becoming sheets, and sheets becoming inverted shapes. But a real neutron star may be messier. It may contain disordered regions, mixed phases, fractures, and irregular structures shaped by its birth, cooling, and magnetic history. The pasta may not be a neat sequence. It may be a crowded, imperfect landscape at nuclear scale. That imperfection may matter for how the star cools. Neutrinos, the nearly weightless particles that carry energy away from dense interiors, can scatter from structures inside the crust. Heat moving from the interior to the surface can also be delayed or redirected by the composition and structure of the crust. When astronomers observe the surface temperature of a neutron star after an outburst, they are sometimes watching the crust relax thermally, cooling as heat diffuses outward. The timing of that cooling can reveal whether the crust conducts heat efficiently or stores it. Hidden nuclear geometry becomes part of the light curve. A telescope sees X-rays. The interpretation reaches down into sheets and rods of nuclear matter. The same hidden structure may influence pulsar glitches in the inner crust. Free neutrons may form a superfluid, and this superfluid can rotate through tiny quantized vortices rather than as an ordinary fluid. These vortices can become pinned to the crustal lattice or to pasta structures, as the outer crust slows with the star's electromagnetic braking. The superfluid may keep rotating slightly faster, storing angular momentum. When enough stress builds, vortices can unpin and transfer motion to the crust, causing a sudden spin-up measured as a glitch. This picture is not settled in every detail, but it shows why the inner crust cannot be treated as a passive shell. It may regulate exchanges between the star's solid exterior and its flowing interior. The timing of a pulsar, read across light years, may carry the signature of neutron superfluid interacting with nuclear pasta beneath the surface. There is also a gravitational consequence. If the pasta layer is as strong as simulations suggest, it may help the crust sustain slight asymmetries that persist despite gravity. A rotating asymmetry would emit gravitational waves, extremely faint but potentially detectable if the object is nearby or distorted enough. The mountain itself would not need to be tall by planetary standards. On a neutron star, even a minuscule elevation can represent an immense mass imbalance. The question becomes whether the crust can hold that imbalance before yielding. Nuclear pasta may raise the answer. It may make the star slightly less smooth than gravity alone would prefer, and that slight imperfection could become a signal. The strongest material in the universe might announce itself not through touch or sight, but through ripples in space-time. Still, pasta is not the core. It is the last complicated boundary before the star moves toward a more uniform interior. Its shapes arise because matter is caught between two identities, no longer isolated nuclei, not yet a continuous sea. That transitional quality gives it power. It is neither ordinary crust nor ordinary fluid, neither chemistry nor simple nuclear matter. It is the place where the star's compression sculpts nucleons into geometry, and where geometry influences astronomy. The inner crust therefore changes the meaning of descent. Moving deeper into a neutron star does not only mean finding greater density, it means finding new kinds of organization forced into existence by pressure. The outer layers removed electrons from atoms. The neutron drip region loosened neutrons from nuclei. The pasta layers begin to erase the roundness of nuclei themselves. Each stage takes away another familiar form and replaces it with a stranger one. Yet even this distorted material may still be only the outer prelude to the deeper question. Beneath the pasta, the structures are expected to dissolve into the core, where matter may become a dense fluid of neutrons, protons, electrons, and perhaps far more exotic particles. There the issue is no longer only what shapes nuclear matter can make, but how compressible the whole star is, how pressure rises with density, and which equation of state decides whether the remnant remains a neutron star at all. Beneath the pasta layers, the neutron star enters a region where shape becomes less important than response. The material is expected to lose the clustered geometry of the inner crust and become a dense core, a fluid in which neutrons dominate but do not live alone. Protons remain in smaller numbers. Electrons and perhaps muons carry charge balance. The particles move under pressures so high that no experiment on Earth can reproduce the full condition for more than a fleeting moment. What matters now is not whether matter forms rods, sheets, or bubbles, but how strongly it pushes back when gravity tries to compress it further. This is the domain of the equation of state. In its simplest meaning, an equation of state tells how pressure, density, and energy relate inside a material. For a familiar gas, that relationship can explain why heating air makes it expand or why squeezing it raises its pressure. In a neutron star, the same general idea remains. But the matter has moved far beyond familiar gas. Temperature is no longer always the leading character. The particles are packed so tightly that quantum rules and nuclear forces may decide the pressure more than ordinary heat does. The equation of state becomes the hidden rule that determines the size of the star, the maximum mass it can carry, the way it cools, and the point at which it can no longer avoid collapse. The difficulty is that the equation cannot be read directly. No probe descends through the crust. No laboratory vessel contains a spoonful of core matter. Astronomers have to infer the rule from consequences at the surface and from the motion of stars in space. Mass is one clue, radius is another, cooling is another. Gravitational waves from mergers add a further constraint, because the way a neutron star deforms just before collision depends on how stiff or soft its matter is. A stiff equation of state means that pressure rises strongly with density, so the star resists compression and tends to have a larger radius for a given mass. A soft equation of state means that matter yields more readily, allowing the same mass to be packed into a smaller radius. These words, stiff and soft, can sound almost mechanical, as though the star were a spring. They are only a shorthand. The real question is how microscopic particles arrange their allowed energies and interactions when crowded into nuclear density across a cosmic body. The core may appear smooth compared with the crust, but it is not simple. Neutrons are fermions, so they still obey the exclusion principle. Even at low temperature, they cannot all fall into the same quantum state. Their crowding creates degeneracy pressure, and their mutual interactions add more pressure or remove it depending on the density and the forces involved. At lower core densities, the picture may be relatively close to neutron-rich nuclear matter. At higher densities, uncertainty grows. The strong nuclear force is well studied inside atomic nuclei, but the core of a neutron star asks about matter with far more neutrons than protons, and at densities beyond the ordinary nucleus. Small uncertainties in nuclear behavior can become large differences in stellar size. A slightly different pressure response in the core may alter the radius by kilometers. It may decide whether a very massive neutron star remains stable or crosses a threshold into collapse. This is why the equation of state is not a technical aside. It is the map of the star's survival. The core also has to maintain charge neutrality and beta equilibrium, a state in which particle reactions settle into balance. If too many neutrons convert into protons, electrons, and neutrinos, or too many of those particles convert back, the composition shifts until the rates balance under the local conditions. In a cold, mature neutron star, most neutrinos escape. So the remaining particles adjust to a stable mixture of neutrons, protons, electrons, and possibly muons. Muons are heavier cousins of electrons. They can appear when the electron energies become high enough that making muons becomes energetically allowed. Their presence changes the pressure and composition, not always in a visible way, but enough to matter in precise models. The deeper lesson is that the core is not a pure sea of neutrons. The name of the star hides a chemical and nuclear negotiation, with each particle species appearing only if the pressure, density, and energy budget permit it. Another complication comes from superfluidity and superconductivity. At the temperatures of a mature neutron star, the core may be cold compared with the energy scales of dense nuclear matter, even though it remains extremely hot by human standards. Under such conditions, neutrons may pair up and form a superfluid, while protons may form a superconducting state. These paired states do not behave like ordinary fluids. A superfluid can move without ordinary viscosity, and rotation in it is carried by quantized vortices. A superconductor changes how magnetic fields move through matter. If these states exist in the core, they affect cooling, rotation, magnetic evolution, and perhaps the timing glitches seen in pulsars. The equation of state must therefore describe more than pressure alone. It becomes part of a larger description of dense matter, including how particles pair, how heat escapes, how magnetic fields are anchored or expelled, and how the interior transfers motion to the crust. A neutron star looks like a compact object, but internally it may be a layered quantum system on an astronomical scale. The observational challenge is severe because different equations of state can sometimes imitate one another. A measurement of mass alone rarely decides the issue. A measurement of radius alone is difficult and model-dependent. Surface emission depends on atmosphere composition, magnetic field, hotspot shape, distance, and light bending by gravity. Binary motion can reveal mass with precision, especially when pulsar timing is available, but radius remains harder. Mergers bring different information. When two neutron stars spiral together, each star is stretched by the gravity of the other. This tidal deformation leaves a mark on the gravitational wave signal. A softer star is generally more compact and less easily deformed. A stiffer star is larger and more easily distorted. By reading the waveform, astronomers can begin to rule out equations of state that make stars too large, too small, too deformable, or too resistant. The merger does not open the star, but it squeezes the answer into spacetime itself. For a brief interval before collision, the hidden compressibility of nuclear matter becomes a gravitational wave pattern. Cooling provides another route. A neutron star is born extremely hot and then loses heat over time, especially through neutrinos escaping from the interior and photons leaving the surface. The speed of cooling depends strongly on which reactions are allowed in the core. Some neutrino-producing processes are slow and modest. Others, such as direct Urca processes, can carry energy away far more efficiently, but they require a sufficiently large fraction of protons and other conditions set by the equation of state. If a neutron star is unexpectedly cold for its age, the interior may be allowing faster neutrino cooling. If it remains warmer than expected, some cooling channels may be blocked or heat may be supplied by magnetic decay or crustal processes. Surface temperature therefore becomes a delayed message from particle reactions deep inside. It is indirect, but it is not empty. The thermal history of a neutron star is another way the core answers without being seen. All of these clues converge on the same hidden relation. For each possible density inside the star, how much pressure is available? Too little pressure, and massive neutron stars cannot exist. Too much pressure, and typical neutron stars become larger than observations allow. The correct equation of state has to pass between these constraints. It must support the heaviest known neutron stars, remain consistent with radius measurements, match cooling behavior, and agree with gravitational wave limits from mergers. This makes the core a place where astronomy and nuclear physics meet under pressure. Particle accelerators can collide heavy nuclei to study dense nuclear behavior for tiny fractions of time. Nuclear experiments can measure neutron-rich isotopes. Theory can calculate interactions from the strong force, but the neutron star itself provides the only long-lived, naturally assembled body of such matter. It is not a laboratory in the human sense, yet it performs an experiment that cannot be repeated elsewhere. Gravity compresses matter and holds it there for ages, while telescopes gather the faint consequences. The equation of state is the translation between those consequences and the unseen core. It is also the gatekeeper for speculation. Before quarks, hyperons, dark matter, or condensates can be considered seriously, they must pass through this rule. They must produce enough pressure to match heavy neutron stars without making all stars too large. They must allow cooling histories that do not contradict observations. They must fit the deformability measured in mergers. The core may contain exotic matter, but it cannot contain any exotic idea without paying the pressure bill. This is why the equation of state becomes the central pillar of the journey inward. It does not reveal the particles by name, but it narrows the space in which they can hide. Beneath the crust, beyond the pasta, the neutron star becomes a question of stiffness, compressibility, and hidden composition. The next clue comes from objects massive enough to make that question difficult. Stars whose measured size seems to resist the expectation that extra mass should always make them shrink. J0740 plus 6620 enters the story not as a visible point of drama, but as a measurement that refuses to sit comfortably. It is a pulsar, a rotating neutron star whose radio pulses allow its mass to be weighed through the motion of its companion. The value that emerged placed it among the heaviest neutron stars known, more than twice the mass of the Sun. That would have made it important, because every very massive neutron star presses against the upper limits of dense matter. But the sharper difficulty came when X-ray observations began to suggest that this object was not correspondingly tiny. Under many softer equations of state, a neutron star carrying so much mass should be squeezed into a smaller radius than lighter stars. Gravity has more material to pull inward, and if the core yields easily, the star should contract more strongly. Yet the measurements pointed toward a radius broadly similar to that of less massive neutron stars. The star seemed heavy without being as compressed as expected. It did not overthrow neutron star physics by itself, because every measurement carries uncertainty. It did something more useful. It narrowed the room in which explanations could hide. The result was a quiet but serious challenge to soft models of the equation of state, those in which pressure rises too weakly as density increases. If matter inside such a star were too easily squeezed, a mass above two suns would likely drive the radius downward or bring the remnant close to collapse. A large radius in a heavy star implies that the interior has found a strong resistance. The core is not behaving like a soft material giving way under added weight. It is pushing back, and the pushback has to come from the particles and forces inside. This is why one star can reshape the argument. Its surface emission, its pulse profile, and its mass measurement together become a test of matter at depths no instrument can enter. The star is not strange because it is large in a simple sense. It is strange because its largeness occurs where compactness was expected. That difference turns radius into evidence. The measurement depends on the way hot regions on the neutron star move through view as the star rotates. NICER observes X-rays from those regions, and the pulse shape is altered by the star's gravity, because the gravitational field bends light. More of the surface can be visible than would be possible around an ordinary sphere. The stronger and more compact the star, the stronger the bending. By modelling how brightness rises and falls across the rotation, researchers can infer combinations of mass and radius. This is difficult work. The shape and location of the hot regions matter. The atmosphere matters. The observer's angle matters. The magnetic field may matter. A radius is therefore not read from the sky in a single clean act. It is extracted from models that must account for curved spacetime around the star. But even with those cautions, the possibility of a heavy star with a relatively large radius carries deep consequences. It suggests that the pressure in the core must increase robustly at high density. That makes some proposed interiors harder to accept. Exotic particles are not forbidden, but they cannot soften the star too much. If they appear, their interactions must restore enough stiffness to keep the star from shrinking beyond the observational limits. This is where the star becomes a filter for the imagination, a quark core, a hyperon-rich core, or any other unusual state cannot be added merely because the density seems high enough. It has to preserve the mass and radius that the universe actually shows. The heavy pulsar therefore changes the tone of speculation. It does not ask only what particles might be possible under extreme pressure. It asks which possible particles can still hold the star open. The distinction is severe. Many exotic forms of matter tend to soften the equation of state because they open new ways for the system to lower its energy. When neutrons can transform into heavier baryons, or when nucleons dissolve into deconfined quarks, the pressure support may weaken unless additional repulsive interactions appear. That weakening once seemed plausible because the central density of neutron stars is so high that new degrees of freedom should perhaps emerge. But massive neutron stars insist on stiffness. They say, in effect, that if the interior changes its ingredients, those ingredients must still create enough pressure. This is the tension sometimes called the hyperon puzzle or the quark matter puzzle. Dense matter theory may predict that new particles should appear, but observed stars demand that their appearance not make the remnant collapse. J0740 plus 6620 is valuable because it tightens that conflict. Its mass alone already forces an equation of state to support heavy remnants. Its radius, if confirmed at the larger end of current estimates, presses further by requiring that support to begin before the star becomes extremely compact. The star does not allow theorists to hide softness only at the highest densities without consequence. It links the hidden pressure profile to a surface scale that telescopes can estimate. The broader population matters as well. Another pulsar, often discussed among the heaviest known, pushes the mass range even higher, though with its own uncertainties. Together, These massive objects form a set of lower boundaries on the maximum mass that dense matter must support. Any equation of state that fails to hold them up is removed. At the same time, gravitational wave observations from neutron star mergers prevent the equation of state from becoming too stiff at lower densities, because overly large stars would deform too strongly during in-spiral. The correct answer has to thread between these demands. It must be stiff enough to carry heavy pulses, yet not so stiff that merger signals and radius measurements become inconsistent. This balance is one reason the problem remains alive. The data does not point toward unlimited rigidity. It points toward a curve, a pressure response that may change with density, perhaps softening in some range and stiffening again in another. Such behavior could hint at phase transitions in the core, where matter changes form without announcing it at the surface except through mass, radius, cooling, and deformation. A neutron star may therefore contain a hidden transition and still masquerade as an ordinary neutron-rich object. A sufficiently strong phase transition could even create so-called twin stars, two neutron stars with similar masses but different radii because their cores belong to different states of matter. This idea remains speculative, but it shows how a single measurement can open more than one path. A large heavy star may mean that the core stays mostly nucleonic and stiff. It may mean that exotic matter exists but interacts repulsively enough to support the remnant. It may mean that a phase transition occurs only beyond the central density reached by that star, or it may mean that the transition is present but disguised by the stiffness of the new phase. The important point is not to choose too quickly. Observations are constraints, not permission for certainty. The star that would not shrink is powerful because it makes vague interiors less acceptable. It forces each proposed core to stand in front of the same simple demand: carry this mass, keep this radius, match the signals. That demand reaches back into the entire journey inward. The crust can shape surface light. The pasta layers can influence thermal and mechanical behavior. The core equation sets the star's global size. But a heavy pulsar brings the global question into sharp relief. The deeper matter may be hidden, yet it cannot hide from gravity. Its pressure determines the radius, and the radius bends the light. The light reaches telescopes, and the pulse pattern returns as a clue. In that chain, the interior speaks through geometry. The mass says how hard gravity pulls. The radius says how well matter resisted. For J0740 plus 6620, the message is not complete, but it is already restrictive. The star remains a dense remnant balanced close to its limit, and still it appears broad enough to resist the simplest expectation of increased compression. Its existence makes the next question unavoidable. If ordinary neutrons and protons can supply the needed stiffness, then perhaps the deepest core is less exotic than the pressures suggest. If they cannot, then the exotic material has to be stranger still, not only appearing at high density, but finding a way to strengthen the star rather than weaken it. The path inward therefore turns from size to substance, from the measurement of a difficult star to the particles that may be unmade at the center. At the deepest density suggested inside neutron stars, the neutron itself begins to look less like an ending and more like a container. It is not fundamental. Like the proton, it is made of quarks, smaller particles bound so tightly by the strong force that they are never seen alone under ordinary conditions. A neutron contains one up quark and two down quarks. A proton contains two up quarks and one down quark. In the world of atoms, that difference helps decide charge, nuclei, chemistry, and the familiar structure of matter. In the core of a neutron star, the difference may become less secure. The pressure rises toward a regime where neutrons are packed so closely that their individual boundaries may overlap. If that happens, the question changes from how neutrons resist gravity to whether neutrons remain intact at all. They may dissolve into a broader state of quark matter, a dense sea in which the quarks are no longer confined inside separate protons and neutrons. This possibility is compelling because it follows the inward logic of the star. Every previous layer has taken apart a familiar form. Atoms lost their electrons. Nuclei became neutron-rich. Neutrons escaped from clusters. Nuclear shapes stretched and flattened in the pasta region. The core may carry that dismantling one step further, undoing the nucleons themselves. Yet quark matter is not an easy answer. To break the ordinary confinement of quarks requires changing the energy balance of the material. The strong force is not weak. It holds quarks inside protons and neutrons with extraordinary persistence, and the transition to deconfined quark matter depends on conditions that are still uncertain. Dense matter theory can describe possible phases, but it cannot simply announce which one nature chooses at the center of a neutron star. If quarks appear too readily, the equation of state may soften, because the material gains new ways to rearrange itself at lower energy. That softness can be dangerous. A soft core yields more to gravity, reducing the radius and lowering the maximum mass the star can support. But massive neutron stars exist. Any quark phase inside them must therefore be compatible with a star that still holds itself open at more than twice the mass of the Sun. This is why quark matter has moved from a simple expectation to a constrained possibility. It may be present, but it cannot merely weaken the remnant without offering another form of resistance. Some models allow quark matter to become stiff again at higher densities through strong repulsive interactions between quarks. Others suggest that quarks may pair in special ways, producing color superconducting phases, where the word color refers not to visual color, but to the type of strong force charge carried by quarks. In such a state, quarks near the deepest core could organize into paired patterns, changing the pressure, heat capacity, and cooling behavior of the star. These ideas are speculative in the careful scientific sense. They are not invented without reason, but they remain dependent on observations that have not yet settled the matter. The evidence required would not be a direct view of quarks. It would be a pattern of mass, radius, cooling, and gravitational wave behavior that ordinary nucleonic matter cannot explain. Hyperons offer another path into exotic density, and they create their own difficulty. A hyperon is a baryon, a particle made of three quarks like a proton or neutron, but with at least one strange quark in its composition. Strange quarks are heavier than up and down quarks, so they are not part of ordinary stable matter. In high-energy experiments, hyperons can be created, but they decay quickly. Inside a neutron star core, the situation may differ. When the energies of crowded neutrons grow high enough, it can become favorable for some matter to transform into hyperons. This would allow the system to relieve pressure by opening new particle states. On paper, that sounds natural. In practice, it leads to the hyperon puzzle. If hyperons appear in large numbers, they often soften the equation of state. The star becomes more compressible. The maximum supported mass can fall below the masses of heavy pulsars already observed. The particles that seem physically reasonable at high density may make the star too fragile to exist. The puzzle is not that hyperons are impossible. It is that their appearance must be balanced by interactions strong enough to keep the core stiff. Without that extra repulsion, the theory conflicts with the sky. This is the recurring discipline imposed by neutron stars. The interior is allowed to be exotic only if the whole object remains stable. Strange matter takes the speculation further. If strange quarks join up and down quarks in a dense, stable mixture, the result could be strange quark matter. Some hypotheses suggest that this mixture might be more stable than ordinary nuclear matter under sufficient pressure. If so, an object made largely of it could be a strange star. not merely a neutron star with a quark core. Such a body might have a different surface structure, a different mass-radius relation, and different behavior in collisions. The idea is fascinating because it proposes that what looks like a neutron star from afar might belong to another family of compact objects. But the same caution applies. No confirmed strange star has been identified. The possibility survives because some observations leave room for unusual compact matter, not because the case has been closed. A strange star would need to imitate many neutron star properties while differing in subtle but measurable ways. It would need to fit pulsar timing, thermal emission, burst behavior, and merger constraints. It would also need to explain why ordinary matter does not simply convert everywhere into the strange state under common conditions, which would contradict the stability of the matter already known. The conversion problem gives strange matter its most unsettling implication. If strange quark matter were absolutely stable, then small fragments called strangelys might, in theory, seed the conversion of ordinary nuclear matter into the strange phase. Such fragments have been proposed in discussions of compact star collisions and early universe relics, but this remains highly speculative, and there is no observational evidence that strangelys are drifting through space transforming matter on contact. The absence of such evidence matters. It keeps the idea within the realm of constrained possibility rather than cosmic certainty. In a calm accounting of neutron star interiors, strange matter is not a horror story. It is one proposed answer to the pressure problem, powerful because it changes the identity of matter itself, limited because nature has not yet supplied the decisive sign. Quark matter, hyperons, and strange matter all share the same attraction. They arise from the recognition that nucleons may not be the final form of dense matter. At extreme pressure, the categories that work in ordinary nuclei may become temporary. New particles may appear, old particles may dissolve, the core may pass through a phase transition, changing its internal state while the outer star remains outwardly similar. But they also share the same burden. Each new ingredient tends to modify the pressure. Each must match heavy masses, plausible radii, cooling histories, and merger signals. The more exotic the proposal, the more carefully it has to survive ordinary evidence. This is what makes the center of a neutron star so valuable. It is not a place where speculation escapes physics. It's a place where speculation is pressed until only a narrower set of possibilities remains. The impossible matter inside the star may turn out to be mostly neutrons and protons in a profoundly interacting fluid. It may include hyperons that are held in check by repulsive forces. It may hide a quark core that stiffens at high density. It may contain strange matter in a deeper phase that has not yet revealed itself. For now, each option sits behind the same observational veil. The surface light bends, the pulses shift, the mergers ring through space-time, the cooling stars fade. From those signals, astronomers try to infer whether the deepest matter remains built from neutrons, or whether the neutron has already opened. The next layer of possibility is even less direct, because some proposed influences may not belong to ordinary matter at all. If the star passes through dark matter during its long life, or if paired particles form a collective quantum state in the core, then the safety net resisting gravity may include ingredients that are not visible in the usual particle inventory. Some possibilities for the core of a neutron star begin outside the star itself. A massive star does not live in empty space, even when the darkness around it appears nearly vacant. It moves through the gravitational environment of its galaxy, through gas, dust, radiation, magnetic fields, and perhaps through a larger unseen sea of dark matter. Dark matter is inferred from gravity, not from light. Galaxies rotate as though extra mass surrounds them. Clusters bend background light more strongly than visible matter can explain. The large-scale structure of the universe forms most successfully in models where an invisible component supplies much of the gravitational scaffolding. If some dark matter particles interact weakly with ordinary matter, then stars may collect a small amount as they travel through galactic space. Most of it would pass through almost untouched, but over long periods a fraction might scatter, lose energy, and become gravitationally trapped. In an ordinary star, captured dark matter would sink toward the center. If that star later dies as a supernova and leaves a neutron star behind, some of the captured material could remain buried inside the remnant, adding one more hidden ingredient to an already extreme core. The appeal of this idea is not that dark matter must dominate the star. Even a modest amount could matter if it changes how pressure responds to density. A neutron star is so compact that small additions can have disproportionate consequences. If dark matter collects in the core, it may form its own concentrated component, interacting with the ordinary neutron-rich fluid through gravity and perhaps through other unknown forces. Depending on the particle properties, this could soften the equation of state, hastening collapse, or in some models stiffen it, allowing a massive star to resist compression more effectively. The outcome is not fixed because dark matter itself is unknown. A heavy dark particle, a late dark particle, a self-interacting dark particle, or a bosonic dark particle could each behave differently inside the star. This makes neutron stars potential detectors, though not in the ordinary sense of a machine built in a laboratory. The star becomes a natural trap and amplifier. If dark matter alters its cooling, its maximum mass, its radius, or the outcome of mergers, then the invisible component may leave a visible astronomical signature. The difficulty is separating that signature from all the other uncertain physics already present. A smaller radius might point toward a softer nuclear equation of state, or toward a dark matter core, or toward a phase transition into quark matter. A heavy star with unexpected stiffness might suggest repulsive interactions among ordinary particles, or an exotic dark sector effect, or no dark matter at all. The same measurement can have more than one interpretation. Dark matter therefore enters the neutron star story as a disciplined speculation, not as an easy solution. There is another route to a stranger core, one that begins not with unseen mass in galaxies, but with the difference between fermions and bosons, electrons, protons, neutrons, quarks, and many baryons are fermions. They obey the exclusion principle and resist being forced into identical quantum states. That rule has already carried the script from white dwarfs to neutron stars. Bosons behave differently. They're allowed to share the same quantum state, and under the right conditions, many of them can act together as a single collective system. This behavior was predicted through the work of Satyendra Nath Bose and Albert Einstein, and is known as Bose-Einstein condensation. In laboratories on Earth, such condensates are made by cooling atoms until their quantum behavior spreads out and overlaps. Inside a neutron star, the environment is nothing like a cold laboratory cloud. It is dense, gravitationally crushed, and filled with nuclear interactions. Yet the deeper principle still matters. If bosonic particles or paired particles form a coherent state under extreme pressure, the core could acquire a collective form of support that differs from ordinary neutron degeneracy. The important word is if. A condensate in a neutron star would not be the same delicate laboratory state drifting in a magnetic trap. It would be a dense many-body phase, shaped by pressure, particle masses, interactions, and equilibrium conditions. Pions or kaons have long been considered in some dense matter models as possible condensed particles. Paired fermions can also behave effectively like bosons, because a pair may carry whole number spin, even though each member of the pair is a fermion. In superconductors, paired electrons create a collective state that changes how electric current and magnetic fields behave. In neutron star cores, paired neutrons may form superfluids and paired protons may form superconductors, both of which are already part of mainstream dense matter thinking. More speculative versions ask whether deeper bosonic condensates could appear and change the pressure enough to influence the star's size and stability. The central question is again the equation of state. A condensate often gives matter new ways to lower its energy, which can soften the pressure response. That may make the star more compressible, worsening the same problem raised by hyperons or quark matter. But some models propose that interactions within the condensate, or between the condensate and surrounding matter, could provide additional resistance. If that resistance is strong enough, a condensate-rich core might help support very massive neutron stars rather than doom them. The idea is subtle because the existence of a new phase is not enough. Its pressure must be correct. Its cooling behavior must be acceptable. Its appearance must not contradict the observed masses of heavy pulsars or the gravitational wave deformability of merging stars. It must also fit with the thermal and rotational behavior that may already point towards superfluid and superconducting components. A neutron star does not permit a new ingredient to remain isolated from the rest of the physics. The moment it enters the core, it changes the whole structure. The connection between dark matter and condensates is not accidental. Some dark matter candidates are bosons. If such particles are captured by a neutron star, they could accumulate in the center and form a compact Bose-Einstein condensate of their own. Depending on their self-interactions, this dark condensate might remain stable, alter the star's radius, or in more extreme scenarios collapse into a tiny black hole that could consume the star from within. That last possibility depends on specific particle properties, and the continued existence of old neutron stars already rules out some dangerous versions of the idea. In this way, neutron stars can constrain dark matter even without directly revealing it. If a certain type of dark matter would destroy old neutron stars too quickly, and old neutron stars are observed, then that type becomes less plausible. The star's survival becomes evidence. The absence of collapse says that many possible hidden particles cannot behave in certain ways. This is a quiet but powerful use of compact objects. They test theories by continuing to exist. Still, none of these possibilities should be allowed to float free of the known foundation. The core is first a problem of dense nuclear matter, neutrons, protons, electrons, muons, superfluidity, superconductivity, and nuclear interactions must be understood before darker or more condensed phases can be added with confidence. Dark matter may be present, but it is not required by every observation. A bosonic condensate may form, but it has to compete with many other explanations. The measured heaviness of certain pulsars may suggest stiffness, but stiffness can arise from ordinary repulsive nuclear forces as well as from exotic components. This makes the center of a neutron star less like a hidden chamber, with a single secret, and more like a pressure test, where several possible forms of matter are forced to prove themselves. Each candidate leaves a different combination of clues. A dark matter core might alter mass and radius relations, cooling, merger remnants, or long-term survival in regions of high dark matter density. A condensate might change neutrino emission, heat capacity, rotational coupling, or the maximum mass. A purely nucleonic core might explain the same observations if its interactions are strong enough. The task is to narrow, not to decorate. That narrowing is slowly happening as better measurements accumulate. Each massive pulsar removes equations of state that are too soft. Each gravitational wave event restricts stars that are too large or too easily deformed. Each cooling measurement tests which particles and reactions are allowed to carry energy away. Each X-ray pulse profile refines the possible radii. In that tightening space, dark matter and condensates remain possible only if they help rather than blur the pattern. Their value is not that they make the neutron star more mysterious. The object is already mysterious enough. Their value is that they show how far the question of support can reach, from visible nuclear matter to invisible galactic mass, from exclusion pressure to collective quantum phases. The star that began as a collapsed core becomes a meeting place for some of the deepest unsolved problems in physics. It asks what matter does when fermions are crowded beyond comfort, what bosons might do when allowed to move together, and whether unseen particles drifting through galaxies can leave fingerprints inside the densest stars. Yet even these possible safety nets may have limits. If mass continues to rise, if a merger adds too much weight, or if the central pressure crosses the last stable range, every proposed form of support must face the same final test whether it can hold the star above the edge of a black hole. The final mass limit of a neutron star is not a wall that can be seen. It is a hidden boundary written into pressure, rotation, temperature, and the composition of matter at the center. A light neutron star may spend ages cooling and slowing, its surface gradually dimming while its interior remains locked in dense equilibrium. A heavier one lives closer to the edge. Add enough mass, and every support mechanism inside it must answer more strongly. Neutron degeneracy pressure has to rise. Nuclear repulsion has to contribute. Any exotic core, if present, has to provide stiffness rather than surrender. The question becomes whether the star still has enough internal pressure to balance gravity, or whether gravity has finally reached a density where no stable neutron star configuration remains. This boundary is known as the Tolman-Oppenheimer-Volkoff limit, named for the theorists who first calculated the maximum mass of a cold, non-rotating neutron star in general relativity. The exact value is not a single settled number, because it depends on the equation of state. Change the pressure response of dense matter, and the maximum mass changes with it. A softer core gives up sooner. A stiffer one can carry more weight. This makes the limit less like a fixed cliff, and more like the last allowed shape of a star under a particular law of matter. The existence of heavy pulsars already tells the limit cannot be too low. Some neutron stars weigh more than twice the mass of the Sun, so any equation of state unable to hold them is no longer viable. But the limit cannot be raised without consequence either. If matter were too stiff across the wrong density range, many neutron stars would be larger than observations suggest, and merging stars would deform more strongly than gravitational wave data allows. The maximum mass therefore sits inside a narrowing corridor. It must be high enough to explain the heaviest observed remnants, yet low enough to remain consistent with radii, cooling, and tidal deformation. Rotation complicates the boundary. A spinning neutron star can support slightly more mass than a non-rotating one, because rotation adds a kind of outward effect against collapse. The fastest pulsars therefore may stand above the static limit for a time, not because their matter is fundamentally different, but because motion helps hold them open. A newly formed remnant after a merger may rotate even more rapidly and differentially, with inner and outer regions not turning at the same rate. Such an object can be temporarily supported by rotation and heat, living as a hypermassive neutron star for a brief interval before it sheds energy and angular momentum. The word temporary is crucial. Extra support can delay collapse, but delay is not stability. As the remnant cools, radiates, and slows, it may cross back below the support needed to remain extended. The star then contracts toward the next state. Whether that next state is a black hole or a more exotic compact object depends on what matter can still do under the added compression. Neutron star mergers offer the most dramatic test of this boundary, because they assemble mass faster than any isolated star can accrete it. Two dense remnants spiral together, losing orbital energy through gravitational waves until their surfaces meet and the distinction between them is erased. In the final moments, the tidal pull each star exerts on the other reveals how deformable the matter is. Then the collision drives the material into temperatures, densities, and rotation rates beyond those of old isolated pulsars. Some matter is flung outward in neutron-rich ejecta, where heavy elements can form. Some becomes a disk around the central remnant. Some joins the core of the merged object, pushing it toward or beyond the maximum mass. The aftermath may unfold along several paths. If the total mass is far above the supportable range, the remnant can collapse almost immediately into a black hole. If it is only somewhat above the non-rotating limit, it may survive briefly before collapsing. If it remains below the true limit once rotation and heat fade, it can settle as a massive neutron star. Each path leaves different traces and gravitational waves, gamma rays, kilonova light, and late-time emission. The famous first gravitational wave detection from a neutron star merger showed why this kind of event matters so much. It brought gravitational waves and electromagnetic light from the same cosmic collision, allowing astronomers to connect the motion of dense matter with the glow of radioactive debris and a short burst of high-energy radiation. The timing of the signals confirmed that gravitational waves travelled at essentially the same speed as light across cosmic distance, placing strong constraints on alternative theories of gravity. The shape of the wave also carried information about the stars before they merged. Their deformability was not unlimited. Their radii could not be too large. Their matter could not be arbitrarily stiff. Yet the event did not fully reveal what the central remnant became. It likely formed a short-lived massive object before collapse, but the exact timing remains difficult to prove. That uncertainty is valuable because it points to the missing boundary. The merger did not simply show that neutron stars collide, it showed that the last fraction of a second before and after contact may contain the strongest accessible clues to the maximum mass of cold dense matter. Beyond the Tolman-Oppenheimer-Volkoff limit, the possibilities narrow sharply. One proposed path is that the compression drives matter into a quark star or strange star, where the relevant pressure is no longer mainly from intact neutrons but from deconfined quarks, perhaps including strange quarks. Such an object, if stable, would not be a neutron star in the strict sense. It would be a compact star of a different phase of matter, possibly with its own mass-radius relation and merger behaviour. The idea remains uncertain because it must survive the same demands that govern every dense matter model. It has to support observed masses, match plausible radii, and avoid producing signatures that should already have been seen but have not. Quark stars are attractive as a way to extend compact matter beyond the neutron star sequence, but they are not a guaranteed rescue. The transition to quark matter may soften the equation of state and hasten collapse, unless the quark phase stiffens again at higher density. If it does stiffen, then a hybrid star with a quark core might remain stable, or a separate branch of compact stars might exist. If it does not, the star passes on toward black hole formation. The other path is simpler in name and deeper in consequence. If no pressure can support the mass, collapse continues until an event horizon forms from outside. The object becomes a black hole, a region where escape requires faster than light motion and therefore cannot occur. The material surface disappears from view. Whatever dense matter existed inside is hidden behind the horizon, and the external description becomes mass and spin. This is a profound loss of information for the astronomer trying to understand matter. A neutron star has a surface, pulses, heat, crustal behavior, and merger deformability. A black hole offers a cleaner gravitational object but fewer direct clues about the state of matter that fell in. The transition between them is therefore a threshold not only in nature but in knowledge. On one side, dense matter still communicates with the universe. On the other, the interior is largely sealed away. Yet even black hole formation can inform the neutron star problem. The mass of the remnant, the delay before collapse, the brightness and colour of the kilonova, the presence or absence of extended emission, and the gravitational wave pattern all help reconstruct how long support lasted. A prompt collapse may imply a lower maximum mass or a softer high-density equation of state. A long-lived remnant may imply stronger support. Future detections with clearer post-merger signals could sharpen the limit dramatically. The final mass limit is therefore not only a number, it is a physical boundary that mergers strike in real time. It decides whether a remnant rings briefly as a distorted neutron star, settles into a heavy survivor, converts into a more exotic phase, or disappears behind a horizon. In that sense, the last tipping point of a neutron star is the strictest version of the question that began in ordinary stars: how much can matter resist? Fusion answered for main sequence stars. Electron degeneracy answered for white dwarfs. Neutron degeneracy and nuclear forces answer for neutron stars. Exotic phases may answer for some deeper interval, but perhaps only briefly, and perhaps not at all. At the final threshold, gravity is no longer asking whether matter can change form. It is asking whether any form can still provide pressure quickly and strongly enough. The answer may differ from star to star, depending on mass, rotation, magnetic field, temperature, and composition. But the consequence is always decisive. A neutron star survives only while its interior can maintain a surface against gravity. Once that surface can no longer be supported, the object leaves the realm where matter can be directly tested and enters the darker simplicity of a black hole. The next movement must therefore return to the signals that arrive before that silence, because the only way to know where the limit lies is to listen to the messengers that escape while the star is still able to answer. The interior of a neutron star answers only through messengers that survive the climb outward. No instrument descends through the crust. No sample reaches a laboratory. The core remains sealed beneath gravity, density, and a surface so compact that even light leaves with its path bent and its energy shifted. Yet the star is not silent. It sends information in pulses, in heat, in sudden flares, in the timing of its rotation, and in the ripples released when two dense remnants spiral together. Each signal is incomplete, but together they form a language for matter that cannot be touched. The most patient work is to translate that language without forcing it to say too much. NICER, mounted on the International Space Station, represents one part of this translation. It studies the soft X-ray light from rotating neutron stars, especially the light from hot regions on their surfaces. As a star spins, those hot regions move across view, and the brightness changes in a pattern shaped by gravity. A larger star bends light differently from a smaller and more compact one. A heavier star changes the pulse in another way. By modelling these patterns, astronomers estimate mass and radius together, narrowing the range of possible equations of state. The measurement is delicate because the answer depends on the atmosphere, the shape of the hot regions, the magnetic field, and the angle from which the star is seen. But delicacy does not make the method weak. It means that every assumption has to be carried openly. The same photons that leave a hot surface also pass through curved spacetime, and that curvature turns a distant pulse into evidence about pressure deep below the crust. Other telescopes listen in a different register. Chandra and Newton study X-rays from neutron stars that glow as they cool or flare after disturbance. Cooling is one of the most revealing behaviors because it depends on how energy escapes from the interior. A young neutron star is born with enormous heat, but it loses that heat through photons from the surface and through neutrinos from the core. Some neutrino processes are slow, others are swift enough to drain energy far more efficiently. Whether those fast channels can operate depends on the particles present, the balance of protons and neutrons, the appearance of muons or more exotic matter, and the superfluid or superconducting states inside the star. A neutron star that is much colder than expected for its age therefore becomes a clue to its inner composition. It may suggest that the core allows rapid neutrino cooling. It may point toward a particle population or phase transition that was not included in softer models. Recent observations of unusually cold neutron stars have already removed many possible equations of state from consideration. The cold surface does not reveal the core directly, but it tells which interiors cannot have produced the observed thermal history. In this way, absence becomes information. Less heat than expected can be as meaningful as a flare. Pulsar timing adds another messenger, one built from rhythm. A neutron star with beams of radiation can keep time with astonishing steadiness as it rotates. When that rhythm changes abruptly, as in a glitch, the cause may lie beneath the surface, where superfluid neutrons exchange angular momentum with the crust. The jump in rotation may be small, but it points toward a hidden mechanical coupling between solid and superfluid components. Over many years, timing records can reveal how the star slows, how stable its interior coupling is, and how magnetic braking drains its rotational energy. In binary systems, timing can also weigh the neutron star with high precision. The mass of a heavy pulsar is one of the most unforgiving constraints in dense matter physics. Any equation of state that cannot support that mass has already failed. The pulse is therefore not only a clock, it is a scale, a stress test, and sometimes a seismometer for an invisible interior. Gravitational waves bring the deepest kind of pressure test because they come from the motion of spacetime itself. When two neutron stars orbit each other, each body raises a tidal distortion in the other. The size of that distortion depends on compactness and stiffness. During the final inspiral, the gravitational wave pattern carries the imprint of how easily the stars deform. A soft star is usually smaller and less distorted. A stiff star is larger and responds more strongly. When the stars merge, the signals become even richer, though harder to capture. The brief post-merger remnant may ring at frequencies related to its radius, mass, and internal pressure. Future detectors may hear that ringing more clearly, and with it the equation of state may tighten further. The first neutron-star merger observed through both gravitational waves and light changed the field because it showed that no single messenger is enough. The waves told how the stars moved. The gamma-ray flash showed a relativistic outflow. The optical and infrared glow of the kilonova revealed neutron-rich debris forging heavy elements. Together, they turned a collision into a multi-messenger event, with each signal constraining a different part of the same dense matter story. The connection to gravity itself is also important. Neutron stars are not merely objects inside spacetime. They are strong gravity laboratories with material surfaces. Their orbits, mergers, and light-bending test general relativity under conditions far beyond the solar system. So far, the theory has passed with remarkable strength. The near-simultaneous arrival of gravitational waves and gamma rays from a neutron star merger showed that gravitational waves travel at essentially the speed of light across immense distances, ruling out several alternative theories of gravity. Triple systems containing neutron stars and white dwarfs test whether gravity treats objects of different internal binding energy in the same way, and the results continue to favor Einstein's theory. Yet most physicists still expect that general relativity is not the final word, because it does not merge naturally with quantum mechanics. A neutron star stands close to the border between them. Its structure depends on quantum pressure and nuclear interactions, while its global shape and light bending require relativistic gravity. If a future equation of state is narrowed enough, some theories of quantum gravity may become impossible because they predict the wrong dense matter behavior or the wrong stellar masses and radii. The star then becomes more than an astrophysical object. It becomes a filter for fundamental law. Still, the answer will not arrive as a single revelation. It will come by convergence. NICER and future X-ray observatories refine radii. Radio timing strengthens mass measurements and internal rotation clues. Gravitational wave detectors add merger deformability and, eventually, post-merger oscillations. Cooling studies remove particle reactions and phases that cannot match observed temperatures. Laboratory nuclear physics constrains neutron-rich matter from below, while heavy pulsars constrain it from above. Each method leaves uncertainties, but the uncertainties overlap less with time. That is how the impossible matter inside a neutron star becomes gradually less hidden, not by opening the star, but by surrounding it with independent ways to ask the same question. How much pressure exists at each density? Which particles carry that pressure? Where does matter change phase? How close can a surface remain to a horizon before support fails? The deepest core may be ordinary only in the sense that neutrons and protons remain its main ingredients. Though under conditions so extreme that ordinary becomes a misleading word, it may contain hyperons, quarks, condensates, or dark matter effects, each one constrained by the need to keep heavy stars alive. It may hide a transition that appears only in the most massive remnants or in the brief aftermath of mergers. For now, the most honest conclusion is not that the mystery has dissolved, but that it has become sharper. Neutron stars began as collapsed remnants, the leftovers of massive stars after fusion failed. They have become instruments for studying the limits of matter, gravity, and quantum law. Their surfaces pulse, their crusts strain, their cores cool, their mergers shake spacetime. Across all these signals, the same buried contest is being measured from different sides. Gravity presses inward with relentless clarity. Matter answers through exclusion, nuclear force, collective states, and perhaps deeper transformations still unnamed. Somewhere inside that answer lies the true nature of the densest stable matter in the universe, and perhaps the first trace of the theory that joins the quantum world to gravity. Until then, every neutron star remains a held threshold, not quite a black hole, no longer a living star, and still able to send back evidence from the edge where matter is almost, but not completely, broken. In the end, a neutron star remains less like an answer than a boundary drawn in matter itself. It is the remnant of a star that has lost its fire, yet not its structure. It is the place where atoms have been stripped away, where nuclei have been pressed into strange shapes, where neutrons gather in densities that make ordinary intuition fall quiet, and where the deepest core may still be hiding a change of phase that no laboratory has yet held for long. Gravity has pushed almost everything familiar out of the way, but not quite everything. A surface remains, light still escapes, pulses still cross space, mergers still send ripples through the dark, and in those ripples, in those X-rays, in those small changes of timing and temperature, the interior continues to leave traces. The mystery is not vague. It has become carefully outlined by mass, radius, cooling, deformation, and survival. Each observation removes some possibilities and leaves others standing a little more clearly. Perhaps the deepest matter is mostly neutron-rich fluid. Perhaps it includes quarks, hyperons, condensates, or some quieter form not yet named with confidence. Whatever the answer becomes, it will have to explain how a dead star can remain balanced so close to disappearance. That is the lasting stillness of the subject, A neutron star is not peaceful because it is gentle. It is peaceful only from far away, where the signals arrive as rhythms and faint light. Beneath that calm exterior, matter is still holding its final shape against gravity, and the universe is still testing how much can be endured before the next threshold closes.